Hello everyone, welcome to Relax School. This is our second video on linear programming, and in this video we are going to cover graphical method. Let's get started. Graphical method is used for solving linear programming problems with two or three variables. This is possible in theory, but generally we only use graphical method when we are using two decision variables. This is because it is easier for us to plot one variable in the x-axis and the other variable in the y-axis. Later we follow some steps to solve the graphical method problem. Okay, let's look into the steps involved in solving linear programming problem using graphical method. The first step is to formulate linear programming problem to get objective function and subjective constraints. This we have already covered in the first video, so I'm not going to talk about it in this video. If you want to watch that video, I'm also going to give the link in the description box. You can go and watch the video. The second step is to draw the graphs for each of the constraint. For greater than or equal to type, the region will be above the constraint line. For less than or equal to type, the region will be below the constraint line. The third step is to find feasible region which satisfies all the inequalities. The fourth step is to solve LPP using any of the two methods, which are corner point method or isoprofit method. We are going to follow all these steps to solve the problems in Institute study material. But before that, I want to clarify point number 2 and point number 3. So you can stick around and watch me solving this problem to understand point number 2 and 3. Or you can skip to the point where I will be solving Institute study material that you will be finding in the description. So let me get started with this problem right here. Here we can find an objective function and subjective constraint. And with this, I'll be helping you to understand how to draw the graph and how to find the feasible region. So to draw the graph, first let's write subjective constraint. The first constraint was 3x plus 2y is less than or equal to 60. Right, so I'll be writing in the form of 3x plus 2y is equal to 60, and we are going to bring this 60 to the left hand side. It would become 3x divided by 60 plus 2y divided by 60 is equal to 1. So 3 20s are 60 and 2 30s are 60. So we will find the coordinates y. Here the equation would become x divided by 20 plus y divided by 30 is equal to 1. So these are our coordinates. For x 20 was the coordinate and for y 30 was the coordinate for the first constraint. So for the second constraint, the coordinates would become, let me write it here, 4x plus 6y is equal to 120. So if we bring 120 to the left hand side, it would become 4x divided by 120 plus 6y divided by 120 is equal to 1. So it would become 430s and 620s. So what the coordinates did we get? For x it's 30 and for y it's 20. So these are the coordinates. So let us try and plot this in the graph. This is how you find the coordinates. So for first equation, x is 20. So on the x-axis we will go to 20. For y it's 30. On the y-axis we will go to 30. And we will draw the line. We will do the same for second equation. For x it's 30. On the x-axis we will go to 30. For y it's 20. On the y-axis you will go to 20. And then we are going to draw the line. Okay, this is how you draw the graph. So the first part was over, drawing the graph. The second part is to find the region. If you look closely, these constraints are less than or equal to type. Okay, so for less than or equal to type, the region will be below the constraint line. So what was this supposed to mean? Let me clear this a little bit. So this was the first line, right? So for less than or equal to type equation, the region will be below the constraint line. So if this was the line, below the constraint line, all of this area is the region for less than or equal to type. So if it was more than or equal to type, it will be above the constraint line. So all of this area. But this was less than or equal to, so this would be the area. So for the second equation, the region would be, if this was the line, all of this area below the constraint line is the region. So for every constraint line, we are going to find the region. This will become the second step. Okay, the third step was to find feasible region which satisfies all the inequalities. Okay, this region is specifying us where a specific inequality is satisfied. What it means when it says satisfied? See, look at it this way. If I say x plus y is less than or equal to 5, the answers can be 1 plus 2 is less than or equal to 5, 2 plus 1 is less than or equal to 5, and so on. So all of these regions we are talking about are nothing but solutions which are satisfying this particular constraint. Okay, moving on, we are trying to find a region where both the constraints are satisfied. So in here, if you observe, all this area right here is satisfying both the constraints. Right, all of this area is satisfying constraint number 1 and 2. So this would become our feasible region. So this is what I want you to guys understand before I move on to solving the solutions using corner point or isoprofit method.
So this was third illustration in CMA Final Strategic Cost Management Study Material, which was going to deal with maximization problem solved by using corner point method. So let's look into the problem. One kind of cake requires 200 grams of flour and 25 grams of fat. Another kind of cake requires 100 grams of flour and 50 grams of fat. Find the maximum number of cakes that can be made from 5 kg of flour and 1 kg of fat, assuming that there is no shortage of other ingredients required for making cakes. Formulate LPP based on the information given and solve graphically. So let's find the decision variables first. Here it is nothing but the number of cakes. So we have two kinds of cakes. So number of cakes for first kind is X. Number of cakes for second kind is Y. So this X and Y becomes decision variables. So the second thing we do is write the objective function. See, our objective function was to maximize number of cakes. So we will write maximize Z is equal to X plus Y. It is very simple. So now we are going to write subject to constraints. So for this purpose, let us write a simple table, alright? It would be very easy for us to formulate the problem that way. Here our decision variables are x and y. So we have constraints which are flour and fat, which was a limited resource. Okay, how many kgs of flour does x take? It's 200 grams of flour. How much flour does y take? It takes 100 grams of flour. We have how many kgs of flour for both of it? It was 5 kgs. Because 200 and 100 are represented in grams, we are going to also represent flour in grams here, which would be 5 kgs, so 5000. For first kind, we are going to use 25 grams of fat. So 25 grams we will write here. And for second kind, we are going to use 50 grams of fat. So 50 we will write here. So the total number of fat we could use was 1 kg. So we will be writing 1000 grams of fat. Right, this is what they have given. So now we could simply write subject to constraints using this table. Okay, which would be 200x plus 100y should be less than or equal to 5000. This is regarding flour. And the second constraint on fat was 25 grams of x and 50 grams for each y kind of cake. The total would be 1000 grams. So less than or equal to 1000 grams. This would become our constraint on fat. Moving on, we are also going to write non-negativity constraint. So what would be our non-negativity constraint? Our non-negativity constraint would be x comma y should always be greater than or equal to 0. Why? Because x and y are physical quantities. They cannot be less than 1. It cannot be -1, it cannot be -2 as such. So now we have formulated the LPP. We are going to solve it graphically. Right? What would be the first step? The first step is to plot the constraint lines on the graph. For this purpose, we will be taking the equation 200x plus 100y is equal to 5000. Right? Now we are going to bring this 5000 to the left hand side. It becomes 200x divided by 5000 plus 100y divided by 5000 is equal to 1. 0 zeros cancel and 225's 50. For 100 it would be 50. Yes, that means the coordinate of x is 25 and the coordinate of y is 50 here. So the coordinate of x is 25 and y is 50 here. For the second equation, which was 25x plus 50y is equal to 1000, we are going to bring this 1000 to the left hand side. It would become 25x divided by 1000 plus 50y divided by 1000 is equal to 1, which would mean 25 40s and 50 20s. So here the coordinate of x is 40 and the coordinate of y is 20. So the x here is 40 and the y here is 20. So let us plot this in the graph. So for the first equation, x is 25. So on the x-axis, we will go to 25. For y it is 50, we are going to go to y-axis and we are going to plot 50 here. And now we are going to draw the line. This was our first equation. Okay. For the second equation, x was 40. So on the x-axis, we are going to 40 and we are going to plot it. And y it is 20. So we are going to go on the y-axis and we are going to look for 20 and plot it. Now we are going to draw the line. Yes. Let me just change the colors. Yes, so this would be our second equation. So for the first equation, all of this area is the region where this inequality is satisfied. Because this was a less than or equal to function, all of the region below the constraint line is the solution, satisfying the constraint. So for second inequality, all of this area here is the area satisfying the equation number 2. If it was a greater than or equal to type, it would have been outside the constraint line. It would have been facing the other side of the corner. But because this was the less than or equal to type, you are going to solve it below the constraint line. So the next step was to find the feasible region. The feasible region here was the area which is common to both of the inequalities and which is satisfying both the constraints simultaneously. So all of this area right here is the feasible region. And all of these coordinates will help us solving the problem. So let us actually solve the problem using corner point method. In the corner point method, the way we find the solution was by identifying the coordinates first. So because now you understood what is feasible region, let me just clear this thing. Yes. Now what we are going to do is, for this feasible region, we are going to find the coordinates. Yes. What is the coordinate here? It would be on the y-axis there is 20, on the x-axis it was 0. So the coordinate is 0, 20. In here it would be 25, 0. And this point it would be 20, 10. 20 on the x-axis, 10 on the y-axis. So here the other coordinate would be 0, 0. But we don't usually need this solution because if you observe, the question was to maximize. If you are not producing any cakes at all, it would not make sense for us. Yes. So the thing is, now we found the coordinates. We are going to put these coordinates in the objective function. And whatever coordinate brings us the maximum value, that would be our solution. So what was the objective function? The objective function was simple. It was to maximize x plus y. I'll write it here. Maximize z is equal to x plus y. So for the first coordinate, let us take 0, 20. Yes, x was 0, y was 20. So 0 plus 20, which was 20. The second coordinate, let's just take 20, 10. X it was 20, y it was 10. So 20 plus 10, which was 30. So the next coordinate is 25, 0. So for x it is 25. For y it is 0, which was giving us 25. So the maximum number of cakes that can be produced while satisfying both of these constraints is by producing 20 number of x cakes and 10 number of y cakes. Let us check the answer. Yes, it was the same. Our decision was to produce 20x and 10y. Which brings us to our fourth illustration, which was minimization problem solved by corner point method. So for this purpose, I'm not going to explain it to you how to formulate the LPP. Rather, I wanted to go by very simply. Yes, I want to take objective function here. I want to take subject to constraints here. And I want to directly solve the graphical problem right down here. Yes, this is because I wanted to assume that you guys have known how to create LPP. I want you to understand how you solve different problems, right? So give me a minute and let me gather all the equations first. Yes, now I have simplified the question. Now we have objective function and subject to constraints. Now we will understand how to draw the graph and find the coordinates so that we will solve the problem. So the coordinates for first equation was x is equal to 25 and y is equal to 12.5. For this purpose, what I have done is I've sent this 25 to the left hand side and I found the coordinates. The same I have done for equation number 2 and equation number 3. And I have found the coordinates. Let's just simply plot them. For first equation, x is 25. So let's assume 24 was here. So 25 would be a little bit to the side. And the coordinate y was at 12.5. On the y-axis, there is 12 here. And 12.5 would be a little bit on the top. Now for the second equation, this was our first equation, which was x plus 2y is equal to 25. And now we are going to draw the line. Right? The second equation, the coordinate of x is 16. On the x-axis, we will go to 16 and we will plot it. On the y-axis, we will go to 24. Which would be here. And we will plot it. And now we are going to draw the line. And for the third equation, x is 20. So it is here on the x-axis. And y is also 20. So we are going to y-axis and we are going to find 20. We are going to plot it and we are going to draw the line. So now, I want you to observe carefully what I am going to do. See, unlike maximization problems where the region will be below the constraint line, here the region will be above the constraint line. That means for this orange line, all of this would be the region solving the inequality. For this brown line, it would be all of this area. For this x plus 2y is equal to 25, it would be all of this area. All of these areas are the areas solving the inequality. So what is the feasible region? The feasible region is always the region which is satisfying all the equations simultaneously. So here, if you properly see, all of this area down in here is the common area, because in this area you cannot find anything except the brown line. In this area there is only pink covered, and this area there is only orange covered, and this area it is only orange covered, and this area it is only brown covered. Unlike this, the outer envelope here is the common area which is satisfying all of the constraints. So for minimization problems it is fairly easy, okay? And just like how we solve the maximization problem, we are going to find the coordinates and write it in the objective function, and whatever gives us the minimum value, that would become our solution. I hope you're getting my point. The feasible region would be the region that is above the constraint line, which is also satisfying all the equations or inequalities simultaneously. So this would be our coordinates. Here if we see it, it would be 0, 24. This would be 8, 12. And this would be 15, 5. And this would be 24, 0. So let's write one by one. 0, 24 if we take as our first coordinate, z is equal to 60 into 0 plus 50 into 24. So this would become 0. 50 into 24 is 1200. So this is becoming 1200. And the second coordinate was 8, 12. That gives us z is equal to 60 into 8 plus 50 into 12. 60 into 8 is equal to 480 plus 50 into 12 is equal to 600, which would become 1080. The third coordinate is 15, 5. That is equal to, that implies z is equal to 60 into 15 plus 50 into 5, which gives us an answer of 60 into 15 is 900 and 55 is a 250. So that means it would be 1150. So that means it would be 1150. Okay, now for the last line, let me just write it to the left side. 25, 0. That means z is equal to 60 into 25 plus 50 into 0. 60 25s. The answer would be 1500. So if you look at all the answers, for coordinate 1 it was 1200, for second coordinate it was 1080, for third coordinate it was 1150, and for the fourth coordinate it was 1500. So what was the least among all of this? It would be 8, 12. Right? So for the decision variable x, it would be 8, and for the decision variable y, it would be 12. So we will look if the answer was the same in the question. We've got 1200, 1080, 1150, 1500. The objective was to minimize, and at B we have 8 and 12, which was the right answer. So with this we have completed corner point method. So this is it in this video, guys. In the next video we are going to discuss isoprofit method. But before ending this video, I want to ask you guys a question. What kind of study plan do you have? Feel free to comment it down below. I'm going to meet you guys in the next video. In the meantime, feel free to like, share, and subscribe if you're liking the content.